Hi, my name is Zihao. I will make a video for my final project. My final project topic is credit card fraudulent detection. Before we enter this data set, I believe that credit card and companies should be able to identify fraudulent credit card transactions. In this way, customers will not be charged for unpurchased items. And we want to use this data set to build a model so that we can end fraudulent transaction before it be charged. In this data set, there are 30 future variables and one target variable. The target variable is class variable. In this variable, 1 stands for fraudulent transaction, 0 stands for no more transaction. For future variable, there is time and amount. Time is number of seconds elapsed between this transaction and first transaction in this data set. So which means time variable is not meaningless in this model or in this data analysis. Amount is stand for transaction amount. And the other 8 variable is V1 to V28. This is provided by a principal component analysis score in order to protect the user's privacy. The question we want to find in this dataset that can we identify fraudulent credit card transaction based on the provided principal component analysis. The benefit of this project: identify fraudulent credit card transaction immediately and accurately, and the fraudulent transaction, protecting the safety of credit card transaction, protects the profit of both customer and company. And we want to end the fraudulent transaction before customer has been charged. So we want a really accuracy model. Prepare this data. First of all, we want to read the CSV file of this dataset. The dataset is downloaded from the cargo here, and we just import to the Python. First, we read the head of the data of the CSV file of the data. We could see all variables here and one target variable here. The data has been successfully imported. Then we want to check if there are any value or missing value in this dataset. So I did check the information of the dataset, and also after I checked the information, I found out there is a 284,000 sample in this dataset. This is a big dataset. It may take time when we do the training. Then I use describe function to describe the variable. We can see this is V1 to V28 variables, and amount variable, the maximum amount variable is 25,000. The minimum amount is 0. So this is a big variation. So we might want to reduce the variation of this variable in the future to standardize this variable. Make it has same variation as other 28 variable does. And the next, we want to answer one question: how many fraudulent transactions in this dataset? Well, in order to find this question, we need to make a histogram to see the count of each transaction, to count of normal transaction and fraudulent transaction. We could say there is most of the data is normal transaction. Only a few amount of is fraudulent transaction. So and then I made a percentage graph to say how much percentage in this dataset is fraudulent transaction. The answer is less than 0.2%. of this data is fraudulent transaction. Now, this becomes a problem because this is an imbalanced sample, imbalanced target variable, and this imbalanced sample will affect the learning model and the classifier. In order to solve this problem, we will use smart in the future to balance data, to balance this data to make it has equal amount of normal transaction sample and the fraudulent transaction sample. And the next thing is we make a hypothesis. I think in this data set, V1 to V28 variable, the principal component analysis score is most important variable in this case. We have seen that time variable is not significant, it's not meaningful. Amount seems like it's not a big matter, but it still can affect the model. In hypothesis, the fraudulent card transaction is only affected by V1 to V28 variable, and moreover, fraudulent credit card transaction may also affect by some of the future, may only affect by some of the future from V1 to V28, which means not all of 28 variable is affect this data. So we'll do the further exploration. Then I made a histogram, use as this plot to create a distribution plot of amount variable. We can see that the largest transaction amount is 25,000 each, and most of fraudulent transaction data is centered at about, this is 225,000, 2,000, this 1,000, probably 500 area, 500, 200 to 800 area. Most of fraudulent transaction happening here, and no fraudulent transaction are at large amount. So we might still want to keep amount variable in our final model, because because there is many fraudulent transactions centered at this area. Then I made a histogram for each variable to see general distribution. For most of the variable, most of V1 to V28 variable is normal distribution. You can see it here. So we cannot tell anything more from this distribution plot. Then I made a correlation plot used as heat map. Before we do the heat map, I set a variable called name correlation and use the SNS heat map to do the correlation, to plot the correlation. The darker color and the lighter color means high correlation. Darker means negative correlation, lighter means positive correlation. We could see V1, V3 have really high correlation, V14, as well as V12, V14, V17, and V2, V4, V11 have really positive correlation. And otherwise, V20 to V28 variable have really small correlation with class variable. So maybe these future variable are not important to this data. We don't know. We still need more analysis. Even we might find more like variable importance in machine learning model.
For this part, I have made some mistake. I did misclick run this distribution again, since I have reduced some variables, and I changed the normal data set, so it shows some error code here. But these are the graph I have plotted before, so it keeps the graph even though this shows some error code here. So just ignore this error code. For this part, I have plotted like this part 1 is the blue, the federal detection and the federal transaction is blue, showing as blue with being with 50, and normal transaction showing as 0 with no being with 100 distribute as yellow or orange graph. In here, we could see there are some variables that shows the obvious distribution. For example, this V11, the federal the normal transaction are centered as this area, but the federal transaction is centered as this part. There are still have variables such as V4, normal transaction over this area, but the federal transactions over this area. From here, we could see there are some variables that have like significant distribution and significant meaning to this model, and some variables such as like V24, V25, V26. Those variables we cannot say there is any difference between federal transaction and normal transaction, such as V20, V21. Those are like centered at 0 and has like normal distribution. And so we could say variables such as V20, V21, V23, etc. it's not that meaningful to this model. And we could also say that while I have listed those variables have not significant distribution, we will leave this here, and after we done variable importance, we could eliminate some of them from the model. Yeah, now I write the for loop here to create the graph for 28 times for each variable, 28 graph in total. And before we enter the machine learning algorithm, I did sort class variable and sort all 0 sample together and sort all 1 sample together. And then I dropped the time because, as I said before, time is not meaningful to this model. Then I did standardization for amount variable. We could see here, before we do the standardization, the variance is huge. And I want to reduce this big variance, so I did standard scale and named it as normalized amount, and the new variable created here with in 1 and -1 range. And then I did smart for balanced sample data, balanced with y variable into equal amount of negative sample and positive sample. I showed the balanced data here. The total sample size is 568,000, and the net positive sample is showing as 284, and negative sample also shows at 254. So in this step, I create balanced data with with positive and with equal amount positive sample and negative sample. Then I did drop the amount for the x value, and I keep the normalized amount variable. I drop both class and amount, and with var variable, I keep the class variable. And then I do the split train with the sample test size to 20%. test size. First, I run the random forest. Oh, in this step, it may create a lot of noise so that may cause this model overfitting. But this is better than, even though this is better than imbalanced data, because if we have imbalanced data, we cannot run the machine learning. The training score is really it's not accuracy anymore. So we have to do this, even we will create a lot of noise and results overfitting. But we can adjust our model later. Then I did the random forest classifier and I want to see what's the accuracy score printed out. Then, but after I use random forest, I did the importance variable with key best. After I set it out and I plot this graph showing which variable is more important to this data. After I showing this plot, we could see V14, V11, V12 are some example are some like really important significant variable, as we said before in the distribution plot, and some variables such as 19, 22, V28 is showing as some like not significant distribution. So after in here, I mark them out. I mark them down like V14, V16, V30, V are important feature. And as I said, some variables are not significant in distribution plot, and also showing here it's not significant. The feature importance is really low, so I remove them. I mark them down here, and I remove them in next step. In this step, I create a plot that with feature name with importance, and the model I use is random forest model that I did before. After I eliminate this new variable, I got new x, and I do test split train again. After that, I run the tree classifier and rerun the random forest classifier again by showing the accuracy score here. The final training score is 99.94 and 99.92. Random forest and classifier gives me a general like a range of like what it can be for our future model analysis. Because decision tree classifier is not a complex training model, so its accuracy will a little bit lower. But I just want to see how it's going in this model and in this data set. So I run the decision tree classifier. I got 99.92 accuracy score, and also I rerun the random forest classifier without those variables. The result I get is 99.94. I got a little bit lower accuracy score. In order to this lower accuracy score shows that by eliminate some variable, I can avoid a little bit overfitting. This is plot I create for the decision tree. Then I did cross validation. In this train test score, I use cross validation to get more precise score, trying to get more precise accuracy score. in each step, I rerun the XY for the test weight train with sample size 30%. Again, because I want to do the logistic regression, since this data set is binary target variable with only 1 and 0. So it's better to use logistic regression to get more precise score. And after I do the logistic regression, I want to fine-tune this model to get more precise score. So that's best choice for in this situation is grid search and cross-validation. So I have import grid search CV. This is a function that use grid search and cross-validation together for our logistic regression model, and it will choose setting the parameter in here with list 1, list 2. And it will choose the best parameter combination and find the best parameter for this model, and also get the most precise score for this model. In here, after I run the fit the model and plot the results, the score, I get accuracy rate with 99.92. This is really an accurate model. This is the most best cross-validation score that I can get from this model, from this logistic regression model. From here, we can say this is about the accuracy score that I get from decision tree. So, which means this is a really precise score. With after chooses the parameter, choose the best parameter. And next, I want to do the deep learning, deep neural training for this model. So I import all the data in for X train XY. For X train X test, Y train Y test, and I do the sequential model, and I add 2 hidden layers in this model, in this deep learning model. And I have this one to have this function to plot out the summary, each step I did here. Then I can compile the function with binarial loss, and also optimize it with Atom. So, and then print out the accuracy score. And the train history equals the model fit. And then I set up a function that called show train history to record each train history for 200 times, and mark down each what the accuracy score we got from the first train and until the last train, and showing the plot. Here is the plot I got here. We could say overall model is pretty good, looks pretty good, even though there are some little gaps here, but overall the validation score is above the training score. The validation loss is lower than training loss. So, and the accuracy score I got is 99.94. It's pretty accurate model. And after here, and after I found the accuracy score of this model is 99.94% accuracy. I decide compared to our logistic fine-tuned logistic regression model, this got more precise score. So we want to use this data model for future analysis. To analyze this score, we need to visualize our result. So the method to visualize the result is use confused matrix. Here, first of all, I creating a function that called plot with confused matrix, which include all the prints, all the plot details, all the property of the plots, with like colors such as labels, etc. And then I plot the confused matrix, import in confused matrix, plot confused matrix with our y-test data sample and prediction score from this data model. And the prediction score I create here. After all, this is our result. We could see there is 71,000 data we found is number of transactions, and 73 we detect as pattern detection. The recall matrix score is 67%. It is really high accuracy, I think, for this model. However, we still got 35 pattern detection, but we didn't. Our model didn't detect it, so I call this missed analysis data. And here is 8 normal transaction, but our model recognizes it as a pattern transaction. In here, I call this misjudged data. In different situations, we need different indicator to measure the performance of the model. But in this model, since we are dealing with credit card transaction, our misjudged result will cause our customer lose a lot of money. We don't want this situation to happen, so we want to reduce this number as small as possible. And for here, because if people are doing the normal purchase and we still lock their credit card, it's gonna waste our customer time. So we also want to reduce this time as smaller as possible. So I creating another function that I create a threshold and also creating 9 matrix with different threshold, different scale of threshold to say what's the result. What can we set to get as smaller these two numbers as. So after plot this function, here I did run this. I did create a for loop. In this I said if this threshold in between this range, it will set in one graph. If it's between 0.2 and 0.3, it will count as this graph. If between 0.3 and 0.4, it's counted as this graph. So totally, in this for loop function, is creating 9 functions in total. This is a confused matrix plot as we did before. In here, we could also see the recall matrix from our data with 0.1 precision score. We got really high accuracy score, and with really high threshold, we got really low accuracy score. In this case, missed analysis data is become more serious issue than misjudged data. So we want to consider this data more. To compare this 9 graph, we saw that with threshold about 0.01, about point 1 has the smallest missed analysis data. However, we got really high missed judgments data because we got this conclusion here, and so in here means the model with the result with smallest missed analysis score is it's a better model and a better result, and also it gets really high accuracy score, which is good. Maximizing the recall of the model is more important than increase the precision. So we might have a lot of data here, but we did eliminate this part of data. Interpretation of this concept, we could find out the precision and the recall are contradictory set of variable. For functions in here, we have once we got smaller threshold, we got higher recall score and a little bit low accurate precision score. But in this case, control the strength of the model we can against the credit card fraudulency. So if company want to find a more credit card fraudulent transaction, smaller threshold is better. In conclusion, this model is quite a bit overfitting. However, we still can generate good output, good result. In actual business, the choice of threshold depends on the company's marginal profit and marginal cost. Less threshold here requires more people to work in this organization, making phone calls with people, checking their credit card status, because we might have a little more misjudgment here. However, with high threshold, there are gonna be more fraudulent transaction happen, less customer experience, and both customer and company will lose their profit. So we basically don't want this thing happen. But if this credit card company is a really small company, there is not much people working with, make phone calls. From here we can say there's only 3 misjudgment. So if a company is a really small company, they could choose a little bit higher accuracy score, such as 0.3, etc., with less misjudgment and a little bit more fraudulent transaction. Okay, thank you.